let's say you have an unknown liquid, and you wish to determine the concentration of this unknown. If you know that it's acidic, or if you know that it's basic, or you have an idea of what reaction will occur, you can carry out a volumetric analysis, or a titration. In a titration, you react a known solution, or a standardized solution, with a solution whose concentration is not known. The known solution, the standardized solution, is called the titrant, and the unknown solution is called the titrant. Or the titrator is the standardized solution, and titrant is the unknown solution. In chemistry, it's particularly useful for determining the pH of an unknown solution, or determining the concentration of an unknown acid or base. And this is actually the subject of our next lab. We'll first start by creating a standardized solution, and then we will determine the concentration of an unknown acid using a standardized solution of sodium hydroxide. This picture shows the basic setup of a titration. You fill a burette with your known solution, and you fill a flask with your unknown solution. And it's even drawn in here to show that the unknown solution typically has a indicator in it. And we'll talk about indicators in just a little bit. But you need to know right now is that an indicator is a weak acid that changes color in the presence of a base. When setting up a titration, it's very important that you take extra care not to allow any liquid, any water, into your burette, because that can affect the standardized solution's concentration. So anytime you're filling your burette in a titration, you want to rinse it out with the standardized solution, all the way from the top, all the way down to the bottom, through what is called the stopcock, which is this little valve at the bottom, down to the tip, needs to be rinsed with your standardized solution. And it's often recommended to do that at least twice. And while indicators were very useful back when I was in high school and in college, the industry has moved away from indicators because they are flawed and they depend upon you to set up your experiment perfectly. Now we typically use pH probes. We will be using both in lab. When the standardized solution and the unknown solution, the unknown concentration of solution, come together, there will be a change in the pHs. And this can be graphed to give us what's called a titration curve. A titration curve shows the pH as more of the standardized solution is added to your unknown concentration. So let's look at this side first. Let's go on the left-hand side first. Right off the back, I can assume I'm starting with an acid in the flask because the graph is starting low. With no standardized solution added, the pH is relatively low in the acid region. In fact, it's really low. So I would probably go out on a limb and say this is a strong acid. And as I add more and more of the standardized solution, it's becoming more and more basic. So I'm assuming that what's in my burette, the drippy part, that must be a base. And if I keep adding more and more, as I add more, the acid is becoming the limiting reagent. So there's a greater decrease in the concentration of hydrogen, and therefore the pH is rising until eventually it reaches a breaking point, and now we've reached something that's alkaline, and we end up with something that's basic. And not only is it basic, it's really basic. This is pretty close to 14. So I would say that what's in our burette is a strong base. On this side, the reverse is true. We're starting with a base, and not only are we starting with a base, we're starting with a really strong base. We're in the strong base region, really high up there in the pH. But as more and more of what is in the burette is added, more and more of the standardized solution is added, our pH begins to fall, so that leads me to believe that our burette contains an acid. And as we add more and more hydroxide is used up until eventually it reaches a breaking point and we start producing an acid. And again, it's a strong acid because this is really, really low on the pH scale. That breaking point where the moles of acid and the moles of base are equal is called the equivalency point. And not only are the moles of acid and moles of base equal, but the moles of the salt they create are equal. So an equivalency point is the point at which the moles of salt equals the moles of base equals the moles of acid. And it's called a couple things. You can call an equivalency point, which is the most common term and probably the one you'll see on your test in the AP exam. But it can also be called an isoelectric point because pH is a measurement of current through, or of minute current through the solution. It can also be called the stoichiometric point. So you'll sometimes see this labeled as equivalency point. You could see it as a dot S, a little dot on the line with an S, and that means they're calling it a stoichiometric point. Or you could see it as a dot I, where it's the isoelectric point. Those are all synonymous terms, and all it means is at this particular point, moles of acid equals moles of base equals the moles of salt. You can find the equivalency point by simply finding the geometric center or the geometric midpoint of the straight line of this curve. So the line starts here, ends here. Midway between the two is this line here, is this point here, the equivalency point. And if we look over, come over, we find that the equivalency point in both of these graphs is a pH of 7, which also confirms my hypothesis that this is a strong acid and a strong base and a strong acid, because that's the only way you could end up with a neutral salt having a pH of 7. Because at the equivalency point, the pH is derived by the salt that they produce. So this is what a graph of a strong acid and a strong base will look like. However, a weak acid and a weak base would be a little different because weak acids will at first not resist the change in pH as much, but then they'll enter the buffer zone. So anytime you see a strong acid and a strong base, or a strong acid, strong base, any combination, you'll see that there'll be a nice flat, or there'll be a gradual slope until you reach just before the equivalency point, and then it'll rise up again. In a weak acid, it'll have this little wimpy curl of a tail down here. And then it will enter what's called the buffer zone, because you now have a buffer that's being created. As soon as that first drop from the burette touches whatever's in your flask, the unknown, as soon as your first drop of standardized solution touches your unknown, you have entered a buffer. You've created a buffer zone. So you'll have a nice wimpy tail for a weak acid or a weak base until you start approaching the equivalency point. But once again, it's the same thing. To find the equivalency point, find the geometric center or the geometric midpoint of that line. So this one is, I'd say, about a little bit before 8. So the pH at the midpoint, or pH at the equivalency point for this would be somewhere, not 8, it would be somewhere about here, at least for the weak acid. It would be around 9, which would make sense. If this is a strong base with a weak acid, the strong one wins, so we're going to end up with a basic salt. Another interesting thing about titration curves is that while the equivalency point tells you where moles of acid equals moles of base equal moles of salt, and the pH is derived from the salt, anytime you have a weak acid or a weak base as a player, you also have what's called a half equivalency point. At half the equivalency point, something very unique happens. The pH actually equals the pKa. Because at this point, the moles of acid and moles of base have begun to equal out, and you haven't produced the salt to a sufficient concentration that you have reached an equivalency point. And if you look at your formula from before, concentration of hydrogen equals Ka times concentration of acid over concentration of base. Well, if acid and base are equal, then concentration of hydrogen equals the Ka. So at the half equivalency point, so in this case, if the equivalency point happened at 25 milliliters, the half equivalency point would be at 12.5 milliliters. So at 12.5 milliliters, we follow our line up, we move over, and we find that the pH is 5. So if the pH is 5, then the pKa is also 5. So we raise 5 to the negative of that. Or sorry, we raise 10 to the negative of that. So the Ka is 1 times 10 to the negative fifth. Very few students who take the AP exam will know this unless they're in the NIMSY program, had their teacher learn from Miss McCormick's videos. So lots of free points you can get here and get that extra lead you need to get that 5. Now you will very, very, very rarely see a titration curve between a weak acid, and I can tell this is a weak acid because it's not down here in the strong acid zone, it's up here. It's up here somewhere where a weak acid we'd expect to start. It also's got this nice little curvy bit, wimpy little tail. And a weak base, again, it's not a strong base. It's not up here by 14. It's like down here. So this is a weak base and a weak acid. You will almost never see this. However, what do we know? How would we explain that a pH of 7 is derived from these two? Well, remember from before. If a strong and a strong produces a pH of 7, because they're going to cancel out, a weak and a weak would also produce a pH of about 7. And in the case of a strong and a strong, I said it came down to their Kas. So if their Kas were Ka and Kbs were relatively equivalent, they would produce a pH of 7. So in the case of ammonium hydroxide, which has a Kb of 1.8 times 10 to the negative fifth, and acetic acid, which has a Ka of 1.8 times 10 to the negative fifth, it's like an arm wrestling contest. Neither one's going to win, and therefore that's the reason we would end up with a salt with a pH of 7. So here we have another graph where we have a strong acid and then a strong base combination, but we're more interested in this weak acid with a strong base. If we were to try to find the equivalency point for this graph here, for the weak acid and the weak base, we could use an indicator. Now, depending on what we were trying to find would determine what indicator would work best. It would look like the geometric midpoint between these two lines here would be this point right about here. So we would probably choose phenolphthalein so that we could determine when this solution has reached its equivalency point, because it will just start to turn pink once we reach that equivalency point. However, if we were trying to determine the half equivalency point, if we wanted to know when our concentration of acid equal our concentration of base, we wouldn't be able to use phenolphthalein because it wouldn't change until much later, until we passed it. So we would want an indicator that changed color somewhere where we could keep track of it. So we would use methyl red. So when choosing an indicator, you want to match it up. You want to match up the Ka of the indicator to the Ka of the weak whatever, either weak acid or the weak base, because that will help you determine when it's going to change color. The Ka is going to help you determine when it's going to change color. So if their Kas match up, they'll both produce this change that is necessary to detect the equivalency point or the half equivalency point. The reason it's the Ka of the indicator is because indicators are just weak acids that change color. They do this because of unpaired d orbital electrons. The point at which the indicator changes color is called the end point, not to be confused with the equivalency point. They are not the same thing. Equivalency point is when moles of acid are equal to moles of base are equal to salt, equivalency. End point is when the indicator changes color. All of the graphs I've shown you have had one increase. They've all had one equivalency point. However, you will sometimes have graphs that have more than one. What would that mean? Well, if all of the ones before this, let's see, we've got acetic acid and sodium hydroxide. Acetic acid is monoprotic, so that must mean that all of these graphs were monoprotic. So if you have multiple jumps, multiple equivalency points, that means you must be diprotic or polyprotic. So this one here would be, I have 1, 2, 3 equivalency points, so this must be a triprotic or a polyprotic acid. And for each dissociation, I could determine, if I use the half equivalency point, the Ka of the first dissociation. I go another half, that's the second dissociation. I go another half, this would be the Ka of the third dissociation. So there are 5 points of interest. There are 5 questions that you'll get about a titration curve on a free response. I could ask you for the pH before you even begin the titration, in which case you just are going to find pH the way we found it on every other problem. You need to do, if it's a strong acid, pH, you need to figure out the concentration of hydrogen, and then do the negative log. If it's a weak acid, you would have to take, do a Rice table. pH on the way to the equivalency point, that's just a fancy way of saying buffers, because you've entered the land of buffers. So we're going to use our same formula. Concentration of hydrogen equals Ka times the concentration of acid divided by the concentration of base. And you're going to add and subtract whatever is being added from the standard solution. Now, whatever the standard solution is, if it's the acid or if it's the base, that's going to start at 0. So this is going to be one of the times where the math department will not like me, because I'm going to tell you to put 0 in the denominator if the base is what you're titrating with, if it is your standardized solution, or in the numerator if the acid is the standardized solution. I could ask you to tell me the pH at the equivalency point. Oh, sorry, I skipped one. pH at the midpoint of the titration, so the half equivalency point. That's probably the easiest of all. Find the Ka. Take the pKa, and that is equal to the pH. Because at that point, the concentration of acid is the same as the concentration of base, and therefore that just comes out to 1. If I want the pH at the equivalency point, you're simply calculating the pH of the salt. So you'll do the hydrolysis reactions that were in the video before this one. And lastly, the pH beyond the equivalency point is really just a limiting reagent problem. You're going to want to keep track of the total volume, because you're going to find the molarity, and you're going to calculate the molarity of whatever's in excess, either the concentration of hydrogen or the concentration of hydroxide, and then use Kw to determine either pH or pOH, depending on what the question asks for. Next class, we'll do essays and free responses on all of this, as well as work exercise 6 from the Buffers Made Easy problems, so that you can see these 5 questions in action.